Okay, good morning, everybody, and welcome to the first lecture of the fourth day of this program. I hope you have enjoyed being here so far. So today I have an announcement to make first. We'll have a shortened first session today. So the first lecture will be from 9:30 till 10:30. Then the coffee break will happen at 10:30, and then again the second lecture will begin at 11. And it will go until 12. So we're going to have 1 hour lectures today in the morning session, and we'll close at 12. Okay, this is just for your information. And regarding Professor Ramurthy's talk, we will have an updated schedule after the morning tea break. So for now, I will hand it over to Michael. He's going to talk to us today about indefinite theta functions.
Okay, thank you so much. I'm happy to join you again this morning. Before we jump into indefinite theta functions, I'm going to start off with a review of ordinary theta functions. I feel like in order to understand really what's going on with our indefinite theta functions, it's helpful to get a grasp on the ordinary theta functions before we get there. And so where do ordinary theta functions come from? Well, primarily, they're products of what's called Poisson summation. Which relies very heavily on the Fourier transform. Okay. So, the idea here, what Poisson summation allows us to do, it allows us a tool to study functions of the form, or constants, identities of the form, some summation of f of n, where n ranges over, say, all of the integers. At least we'll start with something of this form. Or maybe we want to make this a little bit more general. We want to talk about some kind of function, f of x, which is given as a sum of this smaller function, little f of x plus n, again, where n ranges over the integers. Okay. Now, there's several situations where expressions like this or functions like this show up in number theory. Of course, for this to make sense, we have to know certain things about our function here. Okay? And the first thing, and really the main thing that we're going to require here is that f of x should be a Schwartz function. Okay? Which, for our purposes, we're just going to say that this means that it is smooth and rapidly decaying. Okay. Of course, we can kind of expand some things here. We don't always need it to be smooth, but maybe the limit of smooth functions. And then I'm going to be a little bit vague about what I mean by rapidly decaying, but let's just accept that for now. Okay. Essentially, I need it to be decaying fast enough that we get convergence with our expression here. Now, the formula for Poisson summation tells us that this summation here, f of n, as n ranges over the integers, is equal to the sum of the Fourier transform of f, again evaluated n, as n ranges over the integers. Okay. Now, improving the Poisson summation, usually we take the step to move down here to a function of this type. Anyway, a lot of times the function like that is actually what we're interested in. But what does the Poisson summation tell us about a function like this? Poisson summation tells us that this should equal a summation f hat of n times e to the 2 pi I n x. Again, where n ranges over the integers. Okay? So what we're seeing here, shifting shifting our function here by this value x turns into these exponential terms that show up here. Okay? Now, another way of interpreting this is this right here gives the Fourier expansion of our initial function f of x. Okay? Should use a capital F here. Fourier expansion. Okay? And so if I have my function f of x, I know that I can write it as a sum over my integers in a way like this. But what this tells me is that these Fourier coefficients, okay, of this Fourier expansion are just the Fourier transforms of my kernel function, my seed here. Okay. Now, I suppose I'm talking about this Fourier transform. I should at least define it for us. Okay. So we'll say f hat of, let me put a variable z here. This is going to be defined as the integral of our function f of x times e to the minus 2 pi I x z. And then we are going to integrate x from minus infinity to infinity. Okay. Of course, there's various versions of the Fourier transform. This is probably the most common one for number theory. We like having something here where this is now going to be invariant as z. Well, what's that? F of x? Oh, yes. That didn't go through all the way. Yeah. So especially when we're creating a function like this, okay, where we know that this is going to be invariant as x goes to x plus 1, right? That's just shifting the sum. Okay, this is the right Fourier transform to kind of get that right expression to pop out of this. Okay, where we're integrating by these exponentials with the 2 pi I there, because we know either 2 pi I times any integer shift just comes back to 1. Okay, so there we go. This is our formula for Poisson summation. Now, the proof of this is not terribly difficult. It's something that we should probably see at least once. The idea here, if we start with our function f of x, okay, because, I mean, assuming that we know convergence here, we know that this is invariant as you shift x by x plus 1, it has to have a Fourier series. Okay? So we do know that f of x is going to be some kind of summation, c of n, e to the 2 pi I x times n, okay, something of this form. In order to figure out what the Cn is, we do a Fourier integral. Okay, so the C of n is going to be this integral. We'll take f of x, we'll multiply by e to the minus 2 pi I xn. Okay, this will cancel out with our exponential for just the one term that we want. Everything else will have one of these exponential terms that's still there. As we integrate from 0 to 1, that will kill all of those other terms, and that will give us just this Cn. Okay? Now, the key part here is because we know f of x is a sum of something like this, we plug this formula in there. This will be an integral from 0 to 1 with a sum as n goes from, well, as n is in the integers of little f of x plus n, e to the minus 2 pi I, I'm reusing letters again, okay, e to the 2 pi I x n, okay. And now, this is an integral from 0 to 1, but then I'm shifting it by an integer at each step, and so these two pieces right here, I can just incorporate all together to turn into an integral from minus infinity to infinity of f of x e to the minus 2 pi I xn, which, of course, is my, there we go, is my Fourier transform. F hat evaluated at n. Let's see, I lost my dx's all the way through here. Okay. Does that make sense? Is that clear to everybody? Okay. Again, I feel like this is something, maybe many of you have already seen this before, but I feel like it's kind of a fundamental piece to work through to see as you're starting modular forms and number theory. A couple of very important examples of this. I'm gonna go over two examples right here that are going to show up over and over in modular forms. The first one is f of x is equal to 1 over x squared plus a squared, okay, for some fixed constant a. Let's say a is bigger than 0, okay? Now the Fourier transform of this is equal to pi over a e to the minus 2 pi absolute value of a. I guess I said that that's greater than 0, so we'll say minus 2 pi a there. Oh, sorry, I got my absolute values on the wrong spot. Minus 2 pi a absolute value of, so yeah, I want to change my variable for the Fourier transform. There we go. Okay, now this is this Fourier transform, whether you want to compute it directly or you can look this up on tables of Fourier transforms, it's a fairly standard one. It's easy to see. But this, when we plug this into our formula for Poisson summation, this gives us a very important result that we use in modular forms all the time. This is the sum of 1 over x squared plus a squared is equal to pi over a times 1 plus 2 times the sum of, say, k equals 1 to infinity of e to the minus 2 pi a k. And this is known as the cotangent identity. This gives us pi over a, I guess the hyperbolic cotangent of pi a, the way that I've written this. Okay, but this is the identity that we get out of here. Okay, now this is an identity that we use specifically for finding the Fourier expansions of Eisenstein series. Okay. Given that we have these two expansions for this for the cotangent function, we can plug this in when you're trying to evaluate, trying to go from the standard definition of the Eisenstein series to its Fourier expression. Okay. And this works out very easily for that. Where at? Oh, summation here, yes. This is the summation from, that's supposed to be an n, and this is from n equals just n in the integers. Yeah, so we're summing over all of our integers here, okay? And we can convert that into our expression with the exponentials, okay? Good. Now the next one is very important. It will lead us to theta functions and further on to pretty much everything that we're going to do today. This is based on the Gaussian function. Okay. The Gaussian function, the reason why Gauss studied this and found this so interesting here, well, anyway, the reason why we want to why it's going to grab our attention when doing our Poisson summation here has to deal with the fact that the Fourier transform comes back to a very similar expression to our original function. Okay, so our Gaussian function here is f of x is going to equal e to the minus pi ax squared. Okay, of course this shows up all over the place. Normal distributions, I guess that's really where we get our name from. The Fourier transform of this is equal to 1 over the square root of a, 1 over the square root of a times e to the minus pi x squared over A. Okay? So if A is 1, this is actually invariant under the Fourier transform. Okay? At least for the, again, for the normalization that we picked here. When A is not 1, okay, we're just sort of inverting it in place, and then we get this extra piece that shows out over here. Okay? Now when we plug this into our Poisson summation formula, okay, we end up getting that, of course, the sum of e to the minus pi a n squared is equal to 1 over the square root of a times the sum of e to the minus pi n squared divided by a, again, n in the integers. Okay? And this right here gives us, well, the transformation law for the theta function, the ordinary theta function, when we evaluate this at, so tau here, well, if we want this to look like tau, we're taking tau to be I times a, I guess depending on how you think of your theta function, maybe I times a over 2. Okay, and this gives us our transformation. Okay. Okay. Any questions here? Is this something that people are relatively familiar with? Have you seen this before? Okay. Okay. If you haven't, then great. This is good to go over. If you have seen it before, then it's a good review. Okay. Now, this is just a one-dimensional version of our Fourier transform and our Poisson summation. We would like to extend this to higher dimensions. Okay. Let's see. So what we're going to do here, let me actually just modify what I have here. Okay, so this is what I have initially. So what we're going to do to change this, we're going to say f now is going to be a function from, well, so again, a Schwartz function. But we're going to say that f is now going to go from Rn to the complex number. So it's going to be a vector valued function. Okay? And we'll say that the Fourier transform, I plug in a vector here. I plug in a vector z. Okay? On the inside, I'm going to change everything to vectors. Okay? Right here, this multiplication has to become a dot product, and then this is an integral over all of Rn. Okay? Now this dot product here, this is just separating out our variables, and so really this is just a Fourier transform in each dimension individually. Okay? There's nothing really complicated, nothing really fancy going on there. This is just a very nice, compact way of doing all of those Fourier transforms in those different dimensions all at once. Okay. Was there a question? No? Okay, great. Okay, so now what does Poisson summation look like here in these higher dimensions? Okay. Well, we're going to look at, again, if f is a function like this, we're going to have our Poisson summation identity. Our Poisson summation identity. If we take the sum of our function here and we range over every vector in, let's say, Zn, okay, this is going to equal a summation over, again, every vector in Zn, but now with our Fourier transform of the function. Okay. And once again, this can be derived in this form, just one dimension at a time. Okay. Nothing extraordinarily fancy going on there. Okay. Now, a lot of times we're interested in functions that aren't just sums over the integer lattice, but maybe we want to sum over a more general lattice. Okay? So the way that we might do that is we would plug in a matrix here. Okay? That would be one way to do this. I like to think about it using a matrix so that I can always kind of bring it back to this very simple case where I can break it down into these individual dimensions. Okay? But we can always turn this into some kind of summation over a lattice, of course, or a more general lattice. Of course, then we have to modify a couple of other things. Okay? Good. Okay. So let's take a look at what happens with a Gaussian. Again, adjusting our Gaussian a little bit to handle our more general lattice. Okay. So let's let so our Gaussian here. Okay, we are going to let f of our x vector here be e to the 2 pi I, and I'm going to write x transpose mx, okay, vectors here, where m is a real positive definite matrix. Okay, real positive, I guess I should say my dimensions here, we'll say n by n since we're talking about Rn and Zn. Okay, so this is a Gaussian with this right here sort of represents a more general quadratic form, okay, for any more general lattice. Okay. Now, if we want to compute f hat here, okay, we're going to do this, let's see, I'm going to use another board so that I can write my equations down sort of all together. Okay, we're going to compute f hat of our vector z, okay, and this is going to be, using our definition, an integral over all of Rn, e to the minus pi x transpose mx minus 2 pi I x dotted with z, okay, dx. Okay. Now the first thing that we do here is we're going to complete the square. Okay. So this is going to equal, I'll have a term on the outside here that I've got to cancel in just a second, but inside here I'm going to have e to the minus pi, and I'm going to adjust this. I'm going to get x plus my z vector, let's see, z times m inverse, this transpose, times m times x plus z, oh, I got those on the wrong side. M inverse z, m inverse z, okay? Dx, okay, so this is completing the square. If I expand this, this will get me this term. The cross terms give me this over here, but I've got an extra term sitting in there, right? So then I need to factor that out here. And so I'm going to have on the outside an e to the, let's see, e to the pi z m inverse z, m transpose m inverse z. Okay? So there we go there. This is, again, a sum over Rn. Now, I'm doing this integral here. These are all shifted points, but I'm summing over all of Rn anyway, right? So that doesn't matter here on the inside. Okay, this part right here just turns into our ordinary integral over all of Rn, e to the minus pi x transpose mx dx, okay? And, except But yeah, okay. And from here, in order to evaluate this, there's a couple of different ways we could go. We could do a change of variables to diagonalize our matrix. Okay. We could, well, M can factor into two component matrices. We could do that change of variable to get rid of everything completely, and we'll get a Jacobian down here. Okay. But altogether, out of that, we're going to get an E, so we'll have this piece on the outside, e to the pi, z transpose M inverse z. Okay. This will turn into we'll have a 1 over the square root of the determinant of M. And then we can think about this as an integral Rn of e to the minus pi x transpose x dx. But this is just a product of a bunch of terms that integrate to 1. Okay? So this is just going to vanish here. And so this right here is the term that I have left over. Okay, now let's see. In my notes, I've got a minus sign here. So I think, did I make a mistake somewhere in there? Oh, that's where it is. That's supposed to be a minus. What was that? The I. E to the, oh, let's see. Yep, so I'm supposed to have an I here. That's going to deal with that sign. Those are supposed to be minuses. There we go, and then that's where that minus comes from. Yeah. In the first term. Here? So the 2 pi I here comes from the Fourier transform. The first term. That should be just our ordinary Gaussian where we've got an e to the minus pi, not a 2 there. Oh, do I have one over here? Oh, the Gaussian here. Oh, yeah. I'm jumping ahead of myself. There's not supposed to be a 2 pi I, there's supposed to be a minus pi. The 2 pi I is always from the term from the Fourier transform. The Gaussian itself, we always want to have just a minus pi. Yeah, thank you for that. Good. Okay. Did I make any other mistakes? I think we've corrected everything at this point. This looks good. Okay. And so there we go. This is what we get out of this. And so this is our transformation. Okay. And so now when we plug this into Poisson summation, we're able to get our more general theta functions. Okay. I would like to make a couple of small modifications, though, to get there. Okay? Notice everywhere we're working with M and a real positive definite matrix. Okay? We would like to modify this to be able to work with, say, something of the form f of x is equal to, f of x vector here is equal to e to the, instead of a minus pi, I want a pi I and then a tau here. And then, again, our x vector, some m, x vector. Okay? Now, how does this compare to what we just did? Okay? Well, the idea here, okay, if tau is equal to, let's just say IV, let's just assume that it's purely imaginary at the moment, okay, then this part right here is going to turn into my minus pi. I can look at my x vector transpose, and then let's just look at the v times the m part. Okay, so that works perfectly fine if I do something like that. Okay, and then being able to extend tau to not purely imaginary. Okay, this is sort of a variation, sort of a holomorphic variation of this initial Fourier transform. Okay. So we're going to look at expressions of this form. Okay. Let's let Q, I will say of a vector, be a positive definite quadratic form. Okay, from, let's say, Rn to C. Okay. Then, what do we know about this? That means that Q of our x vector has to equal something like our x vector transpose times some matrix A times x, okay, where A is, again, a real positive definite matrix. Okay. Now, associated with our quadratic form, okay, we can have a bilinear form. Okay, since I'm already writing things in terms of matrix, we'll just continue with that. Okay, this bilinear form is going to equal x transpose times A times y, and then let's see. Let's see, we often will, I guess we should put our 2 in there. Okay. So this satisfies that, so our bilinear form of x comma y is equal to the quadratic form of x plus y minus the quadratic form of x minus the quadratic form of y. Okay. So this is just our standard notation. Okay. Again, I like to think about it in terms of the matrix, but if you like to think about it in terms of just these binary quadratic forms, or not binary, but these quadratic forms, then we can always use that notation. Okay. Now our theta function for a given quadratic form, so I'm going to say theta of q as a function of tau is going to equal the sum over, let's say, v vectors inside of our Zn, e to the pi I tau times q of our vector plus, let's see, the way that I have this written, I've got my 2 up here. So we'll continue with this plus pi I of, let's say, z of my binary form. What am I doing here? Pi I times my binary form of a separate z vector with my v vector here. And I should change this. Okay. Okay, so this is going to include this is going to allow us to include sort of a Jacobi variable here, okay, or a vector that could, for instance, include Jacobi terms. Okay. Okay. This is our form here. We can create our quadratic form, and then the Poisson summation nicely gives us our transformation laws for this quadratic form. Okay. Now, the topic of our talk today was indefinite quadratic forms, not these ordinary quadratic forms. Okay. So what goes wrong when we change this up a little bit and allow Q to be an indefinite quadratic form? Let's see. So somebody tell me what goes wrong. For some of you, it's probably obvious. For some of you, it might not be. Anybody Tell me immediately what it is. What's that? The determinant. So, okay, so we could have something with the determinant 0. We could also have a negative determinant. Okay. What goes wrong with the construction? So determinant 0 would cause an issue right here with this transformation. Sure. Okay. What happens if we have a negative determinant? I mean, we could still presumably make something work there with that determinant in the bottom. What else? What else could go wrong? Anybody else see this? Okay. The big issue is that our summation isn't going to converge. Okay? If we have an indefinite quadratic form, this is no longer a Schwartz function. We no longer have this rapid decay that we need in order for the summation to converge nicely. E to the, I'm just going to simplify this, and we're just going to look at pi I tau q of our x vector. We'll just focus on this one. This one no longer decays enough. In at least some direction, it's not going to decay at all. Okay? And so our summation isn't going to make sense. Trying to do the Fourier transform isn't going to make sense. Okay? It's just going to break down all the way around. Okay? So the way that we fix this, the idea to fix this, is to change our function. Okay? We want something kind of based on the Gaussian, but we're going to modify it. So idea, modify the Gaussian. Okay, and so we're going to look at a function, something of the form f of x is equal to. So I want to have this pi I tau q of x term in here. Okay, I want it to look like this, but in order to make things work, we're going to create some other function here. We'll use a 5 for the moment, of our variable, so that this has appropriate decay. Okay, so we need it to have appropriate decay so that it converges, okay? But then also, we want it to behave nicely under the Fourier transform. I'm just going to write f hat, okay? So I want f hat to look somehow similar to f, or at least to have some nice relation that we can work with. Okay? So this is where the theory of indefinite theta functions starts. Now, I have learned about indefinite theta functions primarily through Zwegers' thesis. Okay? Zwegers' thesis is a really nice and very relevant account of indefinite theta functions, especially leading us towards the Mach theta functions that Nick is talked about yesterday and will continue in just a minute, and several other people have talked about. But Zwegers was not the first person to consider indefinite theta functions. Okay? So indefinite theta functions have been studied by Siegel. Hecke has a very nice class of indefinite theta functions connected to real quadratic fields. And very relevantly, we have Zwegers has a very strong theorem from the 70s. In fact, almost all that Zwegers writes about indefinite theta functions is incorporated in Zwegers' work. Zwegers was not aware of Zwegers' work when he wrote his thesis. He became aware of it later, and he's written another paper that kind of relies on Zwegers a little bit more solidly. But Zwegers is very strong, very powerful, and it would be as you're studying indefinite theta functions, it would definitely be a misstep to ignore Wigner's and focus solely on Zwegers' work. Okay? I will very briefly describe Wigner's theorem, but again, because our topic is moving towards the indefinite theta functions, I am going to quickly move into at least Zwegers' notation to set things up for Nick in just a minute. Okay. So what Wigner's does for us is she gives a very nice and clear description of what that function, capital Phi over there, should be in order to get a nice modular transformation. Wigner's describes this Phi function, okay? And in particular, she has an equation that says that this Phi function should satisfy, so delta x plus 2 pi x dotted with the gradient, this acting on phi of x should equal 2 pi lambda phi of x. Okay, and these should all be vectors. Okay. And here, this is a Laplacian, okay, for our variables inside of x, and then of course the gradient. Okay, so Wigner's says that we need our function phi to have this property in order for things to go nicely with the Fourier transform. Okay, and so as long as we have this property and we have sufficient decay, then Wigner's gives an explicit description of the modular transformation explicit description of the modular transformations for our theta function. For a theta function using that quadratic form and our this choice of phi. Okay. Now again, as I mentioned before, I've learned about indefinite theta functions primarily through Zwegers. Okay, and so while I have a great deal of respect for Wigner's theorem, if you ask me a lot of details about this theorem specifically, I am unfortunately not going to have a lot of direct answers for you. Okay. But it is a very powerful, very strong theorem, and one that I certainly intend to study further in the future. Okay. Now, this is going to set us up for Zwegers' description of indefinite theta functions. Okay. Again, so the functions that I'm about to describe are going to have a term that satisfies Wigner's property here. I'm not going to prove that, but they do. Zwegers then spends several pages proving the modular or the Fourier transform, okay, even though he could have done a little bit less work to just show that it satisfies Wigner's theorem directly. And so we're going to use Zwegers' definition here. So what Zwegers defines for us are these theta functions. So he uses this curly theta, A, C1, and C2. And then we're going to get these variables, Z and tau. Okay. Z here is, again, going to be a vector. It incorporates elliptic variables here. We have this, and then this is defined to be e to the I guess, so z is equal to, again, we've got these vectors, a tau plus b, where a and b are real numbers, and as always, tau is in the upper half plane. Okay, so we end up having e to the minus 2 pi I q of a tau minus 2 pi I bilinear of a and b. Okay, again, this is just a decoration out front. Okay, don't worry too much about it. Then we're going to multiply by the summation. This is the sum over the lattice. Z to the, well, let me follow Zwegers' notation here. So he uses R for the dimension, and he's summing over n. Okay, and so what we get here is this function rho, C1, C2. I haven't defined C1 and C2. I'll define those in just a moment. Okay, they're vectors that have important properties here. But then we've got our n vector plus our a vector, tau. So some function here. This is taking the place of that phi function that Vigneris uses. And then we have our exponential term. Okay, I don't want to go on another line. I'm just going to continue forward from here. And then this is the main part here, 2 pi I tau q of n plus 2 pi I b of nz. Okay. Now let's see. This is what I have written in my notes. I feel like this 2 is maybe not supposed to be there. Let's see. Actually, let me really quickly consult Zwegers' paper. I have it right here, because I don't want to leave that with a typo on there. Okay, Zwegers does have that there. Okay, so I will leave that then, because that is in his paper. Okay, so 2 pi I tau quadratic form plus our bilinear form with this piece that has our elliptic variables here. Okay. Now, so this is this description here. Okay. Now, for Nick's talk, we're going to want to modify this notation just a little bit. Again, Zwegers does the same thing, okay, but he writes like this. So we're going to have C1 and C2 down here. Okay, still need to define those. And then he writes this as a function of tau, and then he writes A and B as like superscripts here. Okay. Let's see. And that right there, where A and B are these terms coming from Z. Okay. So this is sort of taking our elliptic variable, but then we're specializing it, and so we're focusing on now some kind of indefinite theta function that is just here on tau. Okay. Now, the pieces that I haven't defined yet, I haven't defined C1 and C2, and this piece right here. Okay. This is our sort of smoothing factor that we want to look at. Okay. So what we have here is C1 and C2. These need to be in, these are vectors in Rn, and they need to have negative norm with respect to this quadratic form. So Q of C1 and Q of C2 need to be less than 0. Okay. Now, there is also a notation, well, let me say less than or equal to 0. If I have them equal to 0, he's got a couple of extra conditions on them, but we'll allow that there for the moment. Okay. Now, there's also another condition. They need to be in the same component, okay, of Rn. Okay, I need to be able to connect them that way. Now, with that, we're going to define, so rho of C1, C2, we at? There we go. Rho of C1, C2 of, let's say, a vector x, comma tau. We break this up into two pieces, one corresponding to each one of these vectors. So rho of C1 of x minus rho of C2 of x. I'll just leave tau implicit here for the moment, where these ones, rho of my vector C, is equal to, okay, well, our standard case is going to involve an error function. We're going to take our error function, we're going to plug in the binary form of C against x, okay, our vector C, that's our index for the function, and then x, the argument that's coming in. And then we divide by the square root of minus q of c, okay? This term simplifies if you take c to have norm minus 1. Of course, that nicely simplifies. And then we do square root of the imaginary part of tau. Let me just say square root of v. And again, this is if the quadratic form of c is less than 0. Okay? Now, if the quadratic form q of c is actually equal to 0, again, there are a couple of other conditions there on c, but I'm just going to brush by those for a moment. In that case, this simplifies dramatically, and we end up just getting the sign of b of c comma x. Okay. So the thing to notice here, well, I guess one thing that I want to point out, in this case, if we choose C1 and C2 so that both of them have quadratic norm equal to 0, then this function it's real. I mean, there's sign values. We're taking differences of ones or minus ones. Okay? And several of the older versions of indefinite theta functions had exactly forms that look like that. Okay? They could be turned into these kind of pieces where you're looking at well, subtracting like a difference of two terms where you've got a sign of something and a sign of another thing. A sign of a dot product with respect to one vector, sign of a dot product with respect to the other vector. Okay? And so this incorporates a lot of those older versions of indefinite theta functions. Okay? The other thing to note here is this error function here. Okay? Zwegers notes that this splits into two pieces, and this is very relevant for his work. Okay? So we have that this error function, I need to follow my notes or I will definitely get this one wrong. So our error function, okay, this is just defined to be 2 times the integral from 0 to z e to the minus pi u squared du. But this is equal to the sine of z times 1 minus beta of z squared, where, okay, now I'm giving another definition, and I know that this starts to get a little bit messy to do definitions on top of definitions here. But this right here becomes a non-holomorphic integral, so from x to infinity, u to the minus 1/2 e to the minus pi u du. Okay? And so what Zwegers notices here is this gives a splitting between a component, a holomorphic piece, okay, the piece that basically contributes to like this down here, okay, and a non-holomorphic component. Okay? And this very nicely lines up with the splitting in harmonic Maass forms between a holomorphic piece and a non-holomorphic piece. Okay? And all that's happening between these two cases is just the sort of limit that you have to take to get to a q of c equals 0 basically kills this beta function component. Okay? Yeah? Right, so we're using this rho function to be the phi that we're talking about there. Okay? So in order to transform it and check all of these variables, there is a calculation involved here. It's not set up directly to look that way. Okay? but there is a calculation there. In fact, that calculation may actually be in Vigneira's paper. I think she may have actually considered a function that is essentially this one. But this is what we get out of this. Okay. Now, I have just a couple of minutes, so I'm going to really quickly do a very interesting example. Oh, question? What's that? Where at? Right here? Oh, this is the bilinear form, V. Oh, yes, sorry, this is the imaginary part of tau. Okay, so let's see. There's no V vectors here. Okay, good. So I haven't used inconsistent notation. V is equal to just the imaginary part of tau. Yeah, great. Yeah. Which one? Sorry, this one right here? Oh, you're right, because Zwegers uses our R and we changed to his notation here. Yes, thank you. Good, good. Any other questions there? Yeah. Sorry, where at? Oh, here? Yeah, so we have this Z vector here that kind of encodes our elliptic variables. Every elliptic variable I can break down into kind of its coordinates. There's going to be right, one component that's kind of in the direction of tau. Okay, so here we might focus at like, so A is going to equal the imaginary part of Z divided by the imaginary part of tau. Okay. At least this is what I would write. Let's see, this is a vector and that's a vector. An imaginary part of tau is a constant. So I can do that. And then B, of course, is the difference. The capital E. Oh, the superscript A here. Oh, this is just a notation. That should be for our quadratic form. Yeah, so that's just that notation there. So Zwegers uses, he writes, again, the quadratic form of some vector x is equal to x transpose ax. Okay, and he uses that at several points. When he explicitly writes out the transformation properties, we need to use that. Okay, let's see. Okay, 5 more minutes. Okay, now I didn't write down the transformation laws. Would you like me to do that really quickly? Okay, so I can either do that or I can do an example. Do an example? Okay, let's do a really nice, easy example. Okay, so this example is going to use A is equal to the quadratic form 1, 2, 2, 1. Okay, so again, this is the A that defines our quadratic form. Okay, we're going to take C1 is equal to minus 1/2, 1/2, and C2 is equal to minus 2, 1. And then we're going to take A is equal to B is equal to 1/6, 1/6. Okay? This is a fun example that Zwegers works out in his paper. Okay? Notice C1 and C2 both have norm. Let's see. So do you C1 and C2 there? 2, 1. Do I have that? I think I have, that's a minus 1. What did I get wrong here? 0, minus 1/2. Yeah, 1/2. Okay, sorry. So these are both in, these both have norm, have negative norm here. So C1 times C1 transpose times A times C1 is going to equal, okay, so minus 1/2, 1/2, 1, 2, 2, 1 times minus 1/2, 1/2. Okay, so this is going to equal, on this side, I'm going to get, so 1 minus 1/2. And so that's going to become a 1/2. And then on this side, I'm going to get a 1/2 minus 1, so a minus 1/2 here, okay, times minus 1/2, 1/2. 1/2 minus 1/2. There we go. Okay, and so now when I do this, this is going to equal minus 1/4. Okay. Now the other one is going to give me something similar. What's that? What am I? Sorry, what was that? This one here? Yeah, okay, minus 1/4. Oh, I've got, yeah, thank you. I've got a minus 1/4 and a minus 1/4. Okay, thank you. Sorry, I'm blanking here at the board. Okay, so we can work this out. So we are falling into this second example. Okay, there are going to be these terms from the non-holomorphic piece, but it actually turns out that they end up canceling, sort of a weird way. Let me just jump ahead here, but the way that they end up canceling, we end up getting, it ends up turning into just this sum of m comma n in the integers. Okay, I'm sorry, I'm stumbling and we need to get ready for the break. So let me just jump ahead here. So when you actually plug this into all of these terms, what ends up coming out of this is this theta function for each of these terms here, the C1, C2, A comma B, ends up turning into 2 times e to the pi I over 3 times eta of tau squared. Okay? And so this is an interesting example where even though these two vectors fall into this higher case, the difference of the beta functions just cancel out completely. You work out the quadratic form that comes out. Actually, Zwegers does this using the transformation properties, and he shows that it ends up equaling this function exactly. Okay? So there's a weight 1 cuss form that is, in fact, an indefinite theta function. Okay, let me go ahead and call that good for today.